Let's jump right into this explainer, because today we're talking about the ultimate automotive rivalry, superchargers versus turbochargers. We're going to break down exactly how these systems force-feed engines to make massive power, and we'll look at the cutting-edge tech that's completely redefining the game right now. Whether you're chasing straight-line speed, heavy-duty towing capacity, or just trying to figure out how modern cars squeeze so much horsepower out of such tiny engines, you are in the right place.
Here's our roadmap for today. 1. The forced induction rivalry. 2. Superchargers, instant mechanical power. 3. Turbochargers, the efficiency kings. 4. Head-to-head performance and durability. 5. Twin charging, the ultimate tag team. And finally, 6. The electric turbocharger revolution. Let's get right into it.
Section 1. The forced induction rivalry, pushing the limits of air. So we all know the foundational problem here. Naturally aspirated engines can only draw in so much air on their own since they're totally at the mercy of atmospheric pressure.
To get more power, we have to artificially squeeze more air into that cylinder. More air means we can add more fuel, right? And that gives us a significantly bigger explosion, which equals way more horsepower, all without actually increasing the physical footprint of the engine. You'll hear the industry call this engine downsizing. It's exactly how a modern 2-liter 4-cylinder can easily crank out the power of a heavy, old-school 3-liter V6, keeping the whole vehicle a lot lighter.
Section 2. Superchargers, instant mechanical power. All right, in the red corner, we've got the absolute OG of forced induction. Believe it or not, a guy named Veltorq bolted the very first functional engine supercharger onto a 2-stroke way back in 1878, literally 19th century tech.
Take a look at the actual hardware of a positive displacement blower. This is a classic Roots type. See those massive heavy metal lobes in there? This whole unit bolts right on top of the engine and is driven directly by a belt attached to the crankshaft. Because it's mechanically tied to the engine's rotation, it's physically pumping huge, fixed volumes of air the exact millisecond you touch the gas pedal.
But as you can see, there are a few different flavors here. The traditional Roots blower basically acts like a big air pump, pushing air into the manifold where it compresses, which honestly generates a ton of heat. Then you've got the twin screw, which is pretty clever because it actually compresses the air internally between those meshed lobes before it even hits the engine, making it run a lot cooler and way more efficiently. And finally, the centrifugal type. It looks exactly like a turbo, but it's belt-driven. Super compact, highly efficient, but unlike the other two, its boost curve goes up exponentially as you climb toward the red line.
Now, going back to those positive displacement superchargers. Because they are directly linked to the crank, throttle response is almost violent. We're talking about hitting 50 kilopascals of boost in a blistering 0.4 seconds, less than half a second. That gives you massive, instant torque right off idle, which is exactly why drag racers and heavy-duty towing guys absolutely love them.
But there's always a catch, right? That instant low-end grunt comes with a serious efficiency penalty. Physically spinning those heavy metal rotors takes a lot of energy. It can actually rob the engine of up to 15% of its total power output just to spin that belt. We call this parasitic loss, and it is the #1 reason supercharged setups are notoriously thirsty for gas.
Section 3. Turbochargers, the efficiency kings. Okay, over in the blue corner, the turbocharger. Now the patent for this goes back to the late 1800s too. But turbos really exploded in popularity during the 1980s. Why? Because they promised to solve that massive parasitic loss problem we just talked about, really paving the way for the modern era of high-performance efficiency.
Instead of stealing mechanical power from the crank with a belt, a turbocharger does something brilliant. It scavenges waste heat energy from the exhaust. As hot exhaust gas exits the block, it's funneled into this housing to spin a turbine wheel. That turbine is connected by a tiny shaft to a compressor wheel on the intake side. It's a beautifully efficient loop that recovers energy that would normally just literally blow right out the tailpipe. But there's a downside here too. Because the turbo entirely relies on exhaust gas volume and velocity to build up pressure, there is a noticeable pause between when you floor it and when the power actually hits. You know it, you hate it, turbo lag. It's been the Achilles heel of this technology since day one. To give you an idea of the sheer engineering extremes we're dealing with, when a turbo is fully spooled and screaming, that internal turbine can be spinning at 150,000 RPM. Think about that. That is roughly 30 times faster than the engine itself is spinning.
Naturally, spinning at 150,000 RPM while being blasted by literal fire from the exhaust creates insane amounts of heat. If you don't manage it, that heat can actually melt the tips right off the turbine blades. Plus, if you shut the engine down while the turbo is still scorching hot, the oil inside the bearings can cook, or coke, turning into a hard carbon, so you're dealing with complex oil cooling lines, super strict maintenance routines, and you almost always need a charge air intercooler just to cool the pressurized oxygen down before it hits the engine.
Moving on to Section 4, Head-to-Head, Performance and Durability. Let's put these heavyweights side by side and see which setup actually makes the most sense, depending on what you're trying to do.
The core difference always comes back to the drive mechanism. The Supercharger's mechanical belt gives you that instant response and monster low-end torque. You step on it, it goes. The Turbocharger, on the other hand, gives you unmatched overall efficiency and an absolute screaming top-end rush. But you gotta wait a beat for that exhaust pressure to build.
When you actually have to live with these systems, things get really interesting. Superchargers are usually an easier install. They bolt on top and use your standard exhaust. But a full replacement? That can run you almost $4,000, and you've got to swap the belt every 50 to 68,000 miles. Turbos are a bit cheaper to replace, averaging around $3,000, but the plumbing is notoriously complex. You need custom exhaust manifolds, extreme heat shielding. Fun fact, if a turbo isn't shielded right, it can literally melt a nearby brake master cylinder. And you absolutely cannot slack on your oil changes.
Section 5, Twin Charging, the ultimate tag team. So what if you're a motorsports engineer and you just refuse to compromise?
How do we get the instant torque of a supercharger, totally eliminate turbo lag, but also avoid parasitic loss at the red line? Back in 1985, the engineers building the Lancia Delta S4 rally car did something completely unhinged to solve this. They looked at the turbo, they looked at the supercharger, and they just said, let's bolt both of them to the exact same engine.
Welcome to twin charging. By teaming them up, the supercharger delivers instant manifold pressure the second you launch, completely masking any hint of turbo lag. Then, while the car is pulling hard on supercharged air, the exhaust gases finally get the time they need to spool up a massive turbo.
The ultimate cheat code here is using an electromagnetic clutch. Cars like the old Toyota MR2 and the VW 1.4 TSI use a clutch to literally turn the supercharger off and decouple it from the belt once the turbo's fully spooled. So you get zero lag off the line and zero parasitic drag at the top end. It's absolutely brilliant. But it is an absolute nightmare of complex bypass valves and custom tuning just to keep the engine from blowing itself apart.
Section 6, the electric turbocharger revolution. Now that wild complexity brings us right into the modern era. Mechanical tricks just aren't cutting it anymore, especially with incredibly strict new rules like Euro 7 and EPA Phase 3 emissions laws forcing a massive evolution in how we boost engines. Enter the electric turbocharger, or e-turbo. Instead of relying purely on a belt or exhaust gas, engineers integrated a high-speed electric motor right onto the turbo's internal compressor shaft. This motor spins the compressor wheel the precise millisecond you hit the throttle, completely erasing turbo lag from existence. Plus, it lets the engine run at a perfect lambda-1 air-fuel ratio all the time, which drastically cuts emissions. Oh, and when you let off the gas, that same motor turns into a generator, harvesting exhaust heat to recharge the car's hybrid battery. Seriously, it's wild. Because this specific tech is so critical to keeping the internal combustion engine viable right now, the market is exploding. Driven by massive suppliers like Garrett Motion and BorgWarner, the e-turbo market is projected to almost double, jumping from about $248 million today to $440 million by 2031. That is a 12.2% growth rate.
It really is a breathtaking fusion of old-school heavy metal and modern 800-volt power electronics. We took a 19th century concept and electrified it for the future. But it leaves you wondering, as these crazy hybrid setups become the standard, is the electric turbocharger the ultimate savior that will keep gas engines alive for decades to come? Or are we just looking at their final, most highly engineered chapter before full electrification takes over? Let that spin around in your head for a bit. Thanks for tuning into this explainer. I'll catch you on the next one.